Good morning. This is part 3 of changing out Nicad batteries for lithium-ion batteries on a DeWalt drill. I've got everything in now to do the conversion, with the exception of the battery management system, printed circuit board. That's not due to arrive until about March 7th. Was the last I heard. So there's not a whole lot I can do except maybe characterize the new battery. This is the new battery, original battery for the DeWalt drill. I can characterize this, and I plan on doing that. This is the original battery that was discharged and can't get it to take a new charge. These are the lithium-ion batteries that I plan to use for the changeover. They're each one of them. They're an 18650 format, 30 amp and 3120 milliamp hour battery. And I've got them in a battery holder right now, and this battery holder is hooked up in a 3S. In other words, 3 lithium-ion batteries hooked up in series. So that's the way they're connected right now. What I plan to do in this episode is I ran across some articles in NASA papers on how NASA reconditions nickel-cadmium batteries. Now NASA has had nickel-cadmium batteries out in space and satellites and on the Mars rovers and that type of thing for years, and they've been able to keep them going for years. And they do it by reconditioning the batteries every so many thousand orbits on satellites, and every so many months when they're traveling in deep space to Mars and that type of thing. And according to the articles I've been reading, if we were to take a nickel-cadmium battery for, say, a DeWalt drill and recondition it about every 2 to 3 months, that it would last for literally years. Now this battery is in a deep state, no charge at all. If I can measure the voltage on this, right now it's showing about, well, 0 volts. There's no charge on the battery at all. What happens to the nickel-cadmium batteries, they get memory, and the memory is caused by crystalline structures changing inside the Nicad battery. And they also can grow dendrites from the anode to the cathode. And the anode and the cathode are just the positive and negative terminals of the batteries that are inside this battery pack. They can grow dendrites that can short out the battery and cause it to lose its charge. So in order to get rid of those dendrites, you can burn them off with a heavy jolt, jolt of electricity. That's what I plan on doing today, and then I plan on reconditioning it. So I'll show you the schematic on how I plan to hook this up. This is a 13.7 volt battery, which is this new battery. It's fully charged and it's measuring 13.7 volts right now. These are each one of the lithium-ion batteries, and they have a 3.4 volt charge on them right now. So I've got them all hooked. I'm going to hook them all up in series, and then have a switch, and this is the dead cell, this cell here. And then I'll have a volt and ohm meter across the dead cell. So what happens is I can close the switch momentarily, very quickly, close it and open it. You don't want to leave the voltage on the dead cell, but you hit it with a charge of, for less than a second. And you do that 3, 4, 5, 7 times. And then while the switch is open, you measure the voltage then on the new battery or the old battery and see if it has any voltage whatsoever. If it has some voltage, then you can put it back in the original charger and see if it starts accepting a charge. If it has a little bit of voltage on it, it may mean that you have burned off some of those dendrites, and it'll start taking a charge again. Now, when they're in this deep a state of discharge, it may be successful bringing them back, and it may not. A percentage of them can't be brought back. NASA does it on a periodic basis, so they never get this bad. So what I'm going to do is I'm going to set this up like this. Now, I've never done this before, so for safety's sake, I'm going to connect this up in the series and with the switch inside this LiPo case in case something happens to the battery while I'm doing it. So that's just a safety precaution. So I will set this up inside this LiPo case, and then I'll be right back. Okay, here it is all hooked up inside the LiPo bag, and now I'm just going to close the switch. I really don't have a switch. I'm just going to connect these two wires together, which is basically the positive of the dead battery, which is this one, to the positive of my series of batteries. And I'm just going to touch them quickly. There's not a whole lot of jolt showing up because I measured the resistance of my dead battery, and the dead battery had a resistance of about 6 ohms, and we've got about almost 24 volts going across here. So 6 ohms resistance and 24 volts is only going to lead to a current of about 4 amps. So it's not going to be a large spark. But the 4 amps ought to be enough. The dendrites that grow are a matter of microns in thickness, so that ought to be 4 amps ought to be enough to fuse those. So now I'm going to open this LiPo bag and measure the voltage across our dead cell and see if we have any voltage on it. And we do. We have 13.6 volts on the cell right now. So I'm going to put that in the charger. Alright, so the old battery is now taking a charge. You can see the light is flashing on the charger. So it is accepting a charge now. When I was measuring the voltage of the battery after I burn off the dendrites, it was losing a charge very quickly, and that's normal. when they've been in this deep state. They don't have any capacity anymore. Their capacity is way down there. So what we're going to do now is we're going to increase that capacity. And the way we do the increase in capacity is we recondition the battery. And you recondition the battery by bringing it up to a full charge, and then you discharge the battery down to about 0.4 volts per cell. Now we have about 10 cells inside this battery pack, so 0.4 volts per cell would be 4 volts. So we drain this battery pack down to full volts from 12 volts. And we're going to do that through a 50 ohm resistor. And this is a 5 watt 50 ohm resistor. So we're going to be putting 12 volts across 50 ohms. So we're going to get about 1/4 of an amp discharge through this battery. Now I see the battery just came up to full charge. So we're going to discharge it and measure its capacity as we discharge. And then we will discharge and charge it up again, and we'll have to do that 5, 6, 7 times, measuring the capacity each time, and see if we can't get to as good as this 3,000 milliamp hour that's on the label or better. So that's what we plan to do next, is we'll recondition this battery. Well, good morning. Well, we partially restored the battery back to normal. I say partially because I only have been able to get about half of the milliamp hours out of this battery, and I ended up with about double or a little more than double of the internal resistance of the battery pack. I've characterized 2 batteries here in this spreadsheet. One is a nickel metal battery, and that's a brand new battery, and I characterized that. I've got stats here for it. Some of the important things are this internal resistance of a brand new battery is running about 376 milliohms of internal resistance, and it can output at stall current of the drill about 16.7 amps is what it can output. Another important thing to look at here is the milliamp hours. The label rating on this battery is 3,000 milliamp hours, and I measured it on a brand new battery, and it's 3,006 milliamp hours, so it's very close to what it should be as a brand new battery. I've also got some data down here as far as clutch testing. On the drill, it has various clutch settings, and I have the amount of current that's being drawn by the drill at each one of those clutch settings when it comes to a stall in those clutch settings. And these are all normal values too. And then if I compare those to the old Nicad battery that I showed you how I brought it back to life by hitting it with a charge, some of the important things to look at there are, again, let's see if I can get this to move over. This is the old Nicad battery that I brought back to life, and the stall current on that is 7 amps when the amateur is stalled, as opposed to the stall current of 16.7 amps for a brand new battery. So you can tell we don't have as much capability from this battery yet. The internal resistance also is 863 milliohms, as opposed to the brand new battery being 376 milliohms. So we have a lot more internal resistance to the battery, also indicating that it's not back up to full charge. And if I look down here at the other stat with milliamp hours. Uh, yeah, milliamp hours. It's running about 1,532 milliamp hours, and it's supposed to be 3,000 milliamp hours. So I'm about half the capacity on this battery. Now, I think what's happening here is I'm just not following the procedure for restoring the battery back to life. That's what I'm guessing anyway. Nickel cadmium batteries, the modern ones, really don't have a memory issue per se. What happens in the modern Nicad batteries is crystal growth. Uh, they, when a brand new battery is available, it has hexagon crystals of cadmium that are measured in microns, about 1 to 2 microns of hexagon-shaped crystals. And over time of charges and discharges and not proper maintenance on the charge and discharge cycles, you can grow crystals of in the 50 microns or better, and those crystals, 50 micron crystals, and those crystals can grow spines, as you might say, and pierce the linings of the battery and actually short out the uh, anode to the cathode and cause draining. And that's what we burnt off with that initial charge of 24 volts and about 4 or 5 amps. We burn off those crystals that had the spines that were shorting out the anode to the cathode. But inside the battery, I would imagine there were still 50 micron or better crystals that were covering the cathode and the anode, so that uh, from the material that causes the charge, so it covers that space, and you can't get as much charge. And what I've been trying to do is discharge the battery and bring it down to about 4.4 volts per cell, uh, and then recharge it again. But I think what I have to do, and what I'm going to try to do this week, is I've only been getting down to about 0.47 volts per cell, and I need to get some different resistor values to slowly discharge. I'll take it down to about 1 volt per cell, or in other words 10 volts for the pack. Take it down to 10 volts for the pack with my 50 ohm resistor, and then after that I would put about a 100 ohm resistor in series and take it down to about 0.4 volts or about 0.47 volts per cell, and then I would throw in a 150 ohm resistor and take it even more slowly down to below that 0.4 volts per cell, and then I'll hold it at that charge for 24 hours, and then recharge it, and then make the uh, measurement again of milliamp hours and internal resistance, and see if I can't come up with a more robust nickel cadmium battery. According to what I've been reading in the NASA newspapers, I should be able to restore this battery back to normal because I have measured the static discharge of this battery, and I'm not getting a lot of static discharge, so I don't have any more of those crystals that are shorting out the anode to the cathode and draining that battery. So I think this 863 milliohms of resistance is being caused by those larger 50 micron crystal structures that won't allow the charge. And I just need to break down those 50 micron crystals into smaller crystals by taking it into a deep discharge and holding it at that discharge for 24 hours. That's what I'm suspecting anyway from what I've been reading. So that's what I'll do as soon as I get the components in, and I'll bring you up to date later on. So please subscribe to my video and like the video, and you can follow what I've been saying and what I've been seeing and measuring. Thank you again.